Thank you, Rafael. Yeah, thank you, everyone. So I think a lot of people know who I am, but for those who do not know, I'm a new postdoc at Berkeley. So that's why I put here perimeter and then the right arrow to BCGP. I am going to talk a lot about older results that I've done during my PhD. So that's why I felt it was good to show that's where I was doing some work. I also thought that we were going to have a very diverse audience. So hopefully I'm going to be talking to not only high energy theorists. So hopefully I'm going to be successful in that, but we'll see. So let me know if you have some questions or even if the language that I'm using sounds a bit different than what you're used to. And again, because I'm going to be talking about older things, I actually decided that, oops, let's see if I can pass. Yes, I can pass. So actually what I decided is that I'm going to do an overview about some properties from these exciting new ideas about complexity in high energy physics. So what I decided then is that I'm going to do an overview about where these ideas come from. And of course, due to the power outage, it's a coincidence that I'm talking about this at Stanford, which is the birth with Lenny Susskind and his group about a lot of these ideas. So thanks, PG&E. And then I put here the second part of my talk, but to be fair, it's more like the last third of my talk. I'm going to say some things that we've been trying to interpret these results in the context of quantum field theory. But of course, quantum field theory is hard, especially CFTs that are strongly coupled and large N. So these results are mostly going to be about Gaussian states and pre-bosonic theories, which of course is not holography, but nonetheless, I think there's still some interesting lessons to be learned there. So this is the plan of my talk. And of course, the first thing that I should start saying is about the AGS-CFT correspondence, which is something that has been inspiring us for the past 20 plus years as of now. And there are many ways to state what AGS-CFT is. And really the way we should think it is that it's a duality between a quantum gravity theory and a conformal field theory without gravity. And of course, this is really a powerful idea because we are very confused about quantum gravity. Sometimes we're also very confused about conformal field theory. And then the duality really gives us an opportunity to learn non-trivial questions on either side. And lots has been learned about it. Of course, that its more precise definition comes from string theory. So actually, I start from string theory, and I go in a certain limit, the AGS5 crosses 5 type 2B. And there's a very precise way that exactly it's a theory that is dual to that type of solution. But here we're going to focus, of course, whenever I talk about holography, it's a more general idea that this should tell us something universal about property of strongly coupled CFTs with a lot of degrees of freedom. And this should be described in a certain limit, essentially by Einstein gravity and quantum fluctuations around it. And this is nice because we can actually calculate a lot of things in this limit. So this is something that we all like. And nonetheless, we're going to learn about this other regime of CFTs that is very hard to make progress using perturbative methods, right? So we're going to be probing this strongly coupled limit of CFT. So here's just a little bit of a cartoon on how we generally think of AGS-CFT that we can describe, for instance, by a gravitational action in AGS in G+1 dimensions. Then I can calculate the equations of motion. I can calculate how the fields they excite perturbations around this background. I can study the back reaction and things like that. And the idea then is that this describes, for instance, the vacuum state of a certain CFT with a certain source that is just coupled to some operators. And then I can calculate expectation values. And this is the dictionary of AGS-CFT. Essentially that, as you can see, I'm relating here fields that are in AGS that has this extra space dimension here. And I'm relating these to sources of the CFT. So this gives me sort of like a more exact mapping between the properties of the CFT and the vacuum of the CFT and these gravitational solutions. So this is sort of the spirit here. And one particular state that we like to study, especially in this field, is the thermal field double state. And if you're coming from a condensed matter quantum information perspective, you've probably seen something like this a lot. And in holography, this is really nice because the space-time that's due to this state is a space-time that has lots of symmetry, and that it's a very fertile sort of like theoretical box to think about AGS-CFT, which is the eternal black hole geometry. I think my colors are not so strong, but hopefully you can see the, yeah, that might be, how do we, oh my God, it's like, let's see how my curtain closing abilities are.
So you gotta pull it this way.
Which way? This way.
Yeah.
Oh, yes, great. Okay. Okay, that's better. Probably it's still a bit light, but yeah, well, probably it's a bit easier to see now. So again, in the spirit of explaining a bit what's happening here, this is a Penrose diagram of a two-sided black hole. So here I have a right boundary and I have a left boundary, and as you can see, they're casually separated. A Penrose diagram is a diagram that tells me about the causal structure of space-time. So in here, I have that light rays always travels at 45-degree angles. So you see that I can't really reach the other boundary without just falling into the interior of the black hole and just collapsing here into the singularity. And the fact that I have two boundaries actually tells that I have two CFTs here, that I have both a right CFT and a left CFT. The thermal field double state means that they are entangled in a special way. And this sort of is a little bit of how we've been thinking, that if I have a certain entanglement structure, this shows in the geometry and how connected the space-time is. It's a bit of the spirit. Also, it's important to say that because this is a copy of the CFT, what I have is that the theory on the right and on the left, they have the same Hamiltonian. And this is shown by essentially this boost symmetry here, that if I do a time evolution here up and here down, I still have the same state. So this is sort of like what the boost on these lines here do. However, there is an interesting regime where it's this green line here, and this is going to be important for the complexity construction that I'm going to talk about later, that I can introduce here some phases. So this is sort of the idea. Also, let me say that the way I should think that's happening in space-time when I draw something like this should be a wormhole like this one, that I connect here a CFT on the right and a CFT on the left. And here, this dot is the bifurcation surface of the black hole. So it means that it's sort of like the size of this disk around the throat of the wormhole. So this is just a little bit of what's happening in this picture. And what's very nice about the thermal field double is that if I try now to trace half of this degree of freedom, I'm going to have just a thermal density matrix. And the thermal density matrix is going to have the temperature of the black hole. And you can see that from essentially Ryutake-Yanagi formula, that this is given by the Bekenstein-Hawking entropy. So it's nice because, in a sense, it's a precise way to see that the Bekenstein-Hawking is giving you like an entanglement entropy in this context between left and right. So, of course, I'm going to talk about quantum complexity, and this is the quantity that we want to study in holography. And this is the insight that Lenny has had, that there is a very interesting connection between the growth of these wormholes and the idea that complexity in certain chaotic circuits, they tend to increase with time. So let me talk a little bit about what, and this from the perspective of high energy theory, it's a kind of different way of thinking about things. So that's why I'm stepping back and trying to see, put some common grounds on what we want to do. So the idea is that imagine I'm given a target state and I'm given a reference state. And the idea is that I just want to build this certain state here in an optimal manner given a set of universal gates. Of course, if I'm talking about qubit systems, I have to give you a tolerance because I want my circuit to end at a certain time. But generally, we're going to be talking about continuous circuits. So this kind of regularization goes away. And then the idea of complexity is something that has to involve a notion of minimization, right? Because it's not enough that I give you a matrix that does this task. I want you to do it in an optimal manner. Also, as you can see, just by this construction, there's sort of a lot of freedom in the way we talk about complexity, right? Because I give you here a reference state, but I could just give you different reference states. I give you here a set of universal gates, but again, of course, that if you're talking from a quantum information perspective, it doesn't really matter, because if you can just simulate these in an efficient manner, then we are fine, right? You don't care so much about the details of your computation that you're doing. And certainly this is the idea with how we're gonna treat this in holography as well. But nonetheless, it's interesting for us to know what is the dependence on certain of these ambiguities that we have. And this is gonna play a big role in both when I talk about the properties in holography and when I talk about the quantum field theory properties. So if it's good for us just to have in mind that this quantity that we are studying is a bit different than other things we've been studying in physics. So the way we usually think about this is that I have to construct a certain unitary that I'm giving a set of fundamental gates. So I can imagine that the gates are just gonna be some operators here that they close an algebra, so I know that given the commutation relation, I can go to any of the directions that I can go to. And because of that, there is a non-trivial path ordering here in this sort of Hamiltonian control problem. And this is why one of the reasons why studying complexity in quantum mechanics is a hard problem. One, because Hilbert spaces are huge, so things get complicated kind of fast. And two is because I have to worry about the commutation relation between all the different directions that I can take in my circuit. And it's kind of hard to show that whatever path you have is actually the optimal path because of that there's not going to be any shortcuts. So in general, this is a very complicated problem. Let me also say that the other thing is that if I do a minimization to this sort of Hamiltonian control problem, I have to give a cost, right? I have to tell you how expensive it is for me to go along the circuit. So this is also something that is sort of like another freedom that we have, which sort of functionals I can put here. I can choose, for instance, that this just follows sort of like an absolute value, and I just sum the absolute values of any of these part of the circuits, or I can give a norm that's like the sum of the squares. So this is something that the answer also depends on it. But again, holography seems, if we want to connect these results to holography, seems to be picking a particular choice for these cost functions. But I'm going to discuss this. I'm going to discuss this later. Yep.
Does locality enter into this at all?
Yes, that's an awesome question, and it's a hard question. So in the constructions that I'm going to show later, we use gates that are local in momentum space, but they're not local in position space. Because when you Fourier transform, they're going to have some non-trivial support. But essentially, this is a technical issue. That it's just that it's kind of hard to impose space locality when you're doing these circuits. I mean, it can be, of course, like it's a numerical thing. But I can give an example, at least in the context of this continuum meta, why these sort of things would be hard. And again, this is the most simple thing one can do.
Maybe more than if it's hard or not, like just should I be thinking about this Ki as a local basis?
Oh, yeah. I mean, in momentum space, certainly. Yes. In momentum space, certainly. In position space, this still has some local support. So it is still within a limit. That's what we're going to do. Also, the idea is that these, of course, if I'm talking about qubits, generally what are good things that I can choose are k-local gates, right? And then I can just choose, I just have two local. And of course, I don't impose a position local, but at least in that sense. So this is also some of the idea here. Yeah. But more concrete, that's a great question. Yeah. Yep.
Not in the continuum, is there a sense, do people know, like, the best algorithm to find the complexity of a state? Do they know that, is there a sense of the worst case complexity of that algorithm?
Of the algorithm itself?
Yeah, that finds the complexity. Like, could it be that that's just like a very...
Isn't that in general very, yeah, I mean, I think that's in general a very hard problem, isn't it?
I think you just have to try every path.
Yeah.
It's almost as bad as that, I think.
Yeah. And then that's exponential, right? In the, yeah. Oh, yeah.
Isn't there
That's
a
true.
limit that's undecidable? for Kolmogorov complexity?
No,
It's what?
I thought there was a version of it that was actually undecidable.
it's Kolmogorov complexity.
Yeah, that's what I said.
Yeah, I think in this
But they're not
case,
definitive.
you can parameterize possible sequences, so you can check them. It's just the number is.
Yeah, it's very hard. Yeah. Very good. Let me just mention this briefly that, of course, there are many ways of exploring this problem. And there's one interesting that particularly from Japan's group, and Masamichi is here, that they sort of study a similar problem, but they're associating a complexity to the path integral and to the path integral geometry. What they're doing is a little bit different than that, but the nice thing about their approach is that a connection to CFT is way more straightforward because we have sort of the same languages. So yeah, bother Masamichi later. So that's, so let me discuss a little bit some of the properties that we expect from complexity to behave in holography. This is a nice discussion in Brown and Susskind paper. That we should really be expecting that this type of circuits, when I do this Hamiltonian evolution, there's a lot of room for the complexity to increase until I go to times that are exponential in the degrees of freedom. And of course, these times are really, really, really huge, right? Remember that generally we're talking about, when you talk about these dynamics, about things that saturate at inverse temperature or the length of the system. And here is exponential on S. And in holography, of course, S is huge because it's proportional to degrees of freedom of my system. And in the limit where we can actually calculate things very precisely in ADS-CFT, this has to go to infinity, right? So this is sort of like the classical regime. And then it's supposed to, whenever I reach these exponentially large times, it's supposed to saturate, and there are just some small fluctuations. And then when I have doubly exponential times, we should expect some sort of quantum recurrence to occur. So then it means that it's also good for me to say that because I'm going to use late times and time goes to infinity in some of the slides to come, but I'm doing holography calculations. So it means that I'm always thinking about these times here, that the complexity is still increasing, right? And here are two properties that I think are essentially two good properties that these complexities should obey. So one of them is this late time growth that's proportional to the energy of the system. Or if I put this in units of the temperature, this really should be related to the degrees of freedom, to the number of entropies that I have. And again, when I'm talking late, I'm still just talking about this phase that this is just increasing. And the second property is this known as switchback effect. And it's essentially a property associated to how hard it is to insert an operator to the past. So it's this idea of the precursor. I'm going to show some diagrams that I can explain a bit better what this happens. But the idea is that you don't really need to do all the extra work to build the time evolution operator back and forth, because there's still a long regime that there's a nice cancellation between the circuit. So the complexity actually is smaller by a scrambling time, essentially, to this calculation. And then one way of seeing this switchback effect in terms of a circuit is to just imagine, again, this is just a cartoon that these are the unitaries that realize the precursor operator. And the idea is that I just insert here a local perturbation in my system that's going to propagate. And as you can see, that it takes sort of like log of the degrees of freedom for this to propagate throughout the whole system. So it means that because the complexity, you don't have to talk about just what is a circuit that prepares, but I have to talk about an optimal circuit. Then it means that for a really long time, we can just give the identity operators, and this approximates well this operator. So that's why we expect that the complexity has this switchback by the scrambling time. So this is a very, and again, this sounds all very, from the circuits and things like that, all very clear, but these proposals there in gravity, and then it's much less clear why gravity has to care at all about these effects. But what's very nice is that there's a gravitational analog to this effect, and I'm going to talk about it later. So, finally, let's talk about how complexity comes in these discussions about ADS. let's look at our thermofield double state again. And I have here my time slice that I prepared the state here. And now what I do is that instead of doing this time evolution upwards and downwards, I evolve with both times up. So that's the green slice. So what it means from the point of view of the state is that I'm just inserting these random phases at each one of these energy eigenstates. So this sort of has a fake time evolution to my system. Of course, the entanglement entropy between left and right, they're always given by the bifurcation surface. So that's not something that we can see. However, we can do this experiment. Or the surface is to just cap off. Only that, the entanglement entropy at this time, it saturates to its thermal volume. So what's interesting about this experiment is that we see that there is some non-trivial dynamics that comes from these wormholes. These wormholes keep increasing and increasing and increasing as I push this longer. Of course, from the Penrose diagram, this is what it looks like. But this is, again, Penrose diagrams, they fool you, they distort distances, but this is an honest calculation that one can do and show that the volume keeps increasing. However, from the point of view of the CFT, it means that there's not really anything happening, that we don't have access to the dynamics that's happening here. So this is when Lenny proposed that complexity should be encoded then in this physics of the wormhole increasing. So here are two precise formulas that is proposed to capture the properties of complexity. So one is called complexity equals volume. And again, complexity equals volume really has the flavor of what I was talking about, because I'm saying that complexity is equal to the volume of the Einstein-Rosen bridge that connects both sides. But then Lenny plus other collaborators here at Stanford, they suggested another proposal called complexity equals action that essentially doesn't take just the extremal surface that connects both sides, but take any essentially any other surface that's connected here. So the Cauchy development of this. So then I have this action that's now bounded by these no rays. And what complexity equals action tells us is that we should evaluate the gravitational action plus matter fields in this big Wheeler-DeWitt patch. And for most of the things that I'm going to talk about complexity equals action. Again, of course, that complexity equals volume still reproduces a lot of these ideas and a lot of these results. However, complexity equals action, there's some nice things about it. First one is that there is no dimensionful ambiguity that I can multiply in front of it, as well as in the volume, if we want to make this dimensionless, other than Planck's length here that I have in G Newton, I have to also worry about an extra length scale, which again, it's fine because we shouldn't worry too much about what is multiplied in front of it and much more about how these things scale. But nonetheless, complexity equals action is nice because once we fix the formula as this, we can talk about it in different spacetimes and compare them. However, I'm going to argue that there are still some ambiguities associated with the complexity equals action, and that these ambiguities actually seem to have some counterpart in some quantum field theory models. So this is what I plan to talk. So complexity equals action, of course, I have to evaluate this gravitational action. As we know, the Einstein-Hilbert action is a two-derivative functional. So it means that in order to have a well-posed principle, I need to put boundary terms such that's going to cancel these other terms that are proportional to the variation of derivatives of the metric. So this is known to be, in the case of time-like and space-like surfaces, this is just the Gibbons-Hawking term that I add to my action. And again, this is going to be important here for the surfaces near the singularity and near infinity. However, this also is bounded by these no rays and by these no joints here that this codimension to. So it's also important for us to know how to deal with these boundary terms. So this is a gravitational paper that was written by gravity people at PI and Rob, who was my supervisor, that they essentially construct some possible boundary terms for these no surfaces. What's interesting about it, though, is that, of course, no hypersurfaces are much trickier because there's not a canonical way that I can normalize my no rays because they have k squared is always 0. But I can certainly make them affinely parametrized. So that's certainly something that I can do to my action. And I can impose that my action has reparametrization invariance as well. So this is what we call this counter term. But we should just think of this as a term that lives in the hypersurface that depends on the data on the hypersurface. So it doesn't change the variational principle. And what's interesting is that even when I add reparametrization invariance to my action, this is still going to depend on a dimensionful coupling because this essentially scales like 1/r. So for this to be dimensionful, I can always just put an L counter term here that doesn't change. So at first, this seems a bit odd because it seems that you're trying to fix a problem that, that there shouldn't be a reparametrization effect on my action, but by doing so, I still add here this arbitrary length scale. And what's interesting is that doing this procedure doesn't seem to be an option. And actually, to reproduce properties of complexity in holography, we actually need to add a term like this. I'm going to talk about these shockwave geometries, but there are other examples where the contributions from these terms are important. One of them, I think it's in this paper by Brian with Matt Hedrick and Cesar, that they discuss subregion complexity in the geometry. So let me talk to you a little bit about some of the results that L counter term appears, or some results that do not depend on L counter term. So the first thing one can study is how of course, the way that these proposals came about is because of dynamics. But nonetheless, if I look at the Penrose diagram, I can calculate, so what's the complexity associated to just this region? And as usual with anything that involves quantum field theory, the answer is infinity. So we are happy, infinity equals infinity, we just go home. But of course, we can do better than that. So what we know is that we can regularize this quantity near the boundary by associating just a UV cutoff in the field theory, and I can calculate what is the leading contribution for complexity equals action. And we find that the leading contribution takes this form, where so 1/delta we should be thinking about here the near boundary expansion. It depends on the central charge, like it should. But then there's this extra scale here. There's this log that, of course, the absolute value should be outside. So this is positive. And I still have, as a leftover, this L counter term divided by LADS. That, again, this just seems to be some ambiguity that is not fixed a priori by the rules of the game. Another property that one can study is this complexity of formation, which is the following, that, okay, we know that this is a UV divergent quantity, but what if I subtract the black hole geometry with 2 copies of the vacuum? Because then we hope that the UV divergence from the black hole spacetime and the ones from these 2 copies are going to cancel each other. And then we're going to have an additional complexity that's just telling me how much harder it is to prepare the TFG with comparison to 2 times the vacuum. So again, this is a gravity calculation. We can calculate. And what we find is the following interesting thing, that we can make these to be UV finite, so it doesn't depend on the UV details here. And also, it doesn't really depend on this L counter term. because essentially all the non-trivial contributions of L counter term that happens in the black hole spacetime and in the vacuum spacetime, they cancel each other. So this thing here now doesn't depend on that. And also another thing is that it's proportional to the Bekenstein-Haken entropy of this black hole. So when I divide CA with this, I have just some coefficient that depends on the dimension, plus some curvature correction. So this is the plenary result. And this looks like a funny function, but if you do a large dimension expansion, this just grows linearly with dimensions. So it's a funny formula, but it's a simple thing. So we see then that the UV divergence, the L counter term appears like this. In the complexity of formation, we can make this finite and just dependent on the entropy of the black hole. And I'm going to come back to this in the field theory results. The other place where we see where this sort of scale appears is in the time dependence of holographic complexity. So now I take this and I time evolve it. And I just plot how this quantity depends on time. Again, this is just a gravitational calculation. I go, I work hard, I put Mathematica, and it gives me this function. Again, the function is simple actually. I can determine for these times as a function of the position of this point. That's where both Wheeler-DeWitt patches meet at the end of the boundary. And when I do so, I see that I have a leftover term here that depends on this L counter term. But of course, this goes to 0 as my times go to infinity. So it means that this goes to 0 when this term approaches the horizon radius. And you can see that I'm plotting here just this function for different values of this ratio of L counter term and LADS. And the interesting thing is that the late time result always seems to be the same. The only thing that you change is this transient behavior here that happens around just the inverse time length scale. So it's a fast transient, and then this goes to the late time value. And again, this is something I want to show in the QFT models as well. So another property that these counter terms are sort of important to me. How am I doing on time? Oh my God, I have to rush. Okay. So the other thing that this counter term does is that it gives the correct switchback effect when I'm looking into the shockwave geometries. So what the shockwave geometries do is the following. Suppose I do an experiment here. This is my two-sided black hole. And what I do is that in one of the sides, I evolve back in times with this time evolution operator. I insert here a perturbation that falls into the black hole, and it back reacts on the geometry. And then I go back in time to here, right? So this is what this precursor thing is doing. So this geometry, I should think of a collapse between a black hole of mass m1 to a black hole of mass m2. And the interesting thing about gravity is that even if this shockwave is made to be very, very, very light, such that I don't really change the mass of the black hole, from the point of view of late time observables, not really the back reaction, but the effect of it can be really big. And this comes because of boost between these large times in this geometry. So what's interesting is that this effect is essentially what gives the switchback effect in this construction. So the quantity I'm going to talk about is how the complexity of performing the precursor in the TFD, and I subtract the complexity that I had before of the TFD. So the thing that I'm calculating should really be telling me how hard it is to insert this shockwave at a pass time minus TW. And this is what I'm going to show you the plots of. And again, this is a completely gravity calculation. This geometry, I can study this with analytically because it's a simple shockwave in this no direction, and I can come and I find nice functions and I expand it, and the result that I have is that this really exhibits the switchback effect. So you see that essentially the scrambling time, it gets bigger as I make this. Of course, the scrambling time is it's proportional to the difference between these temperatures here that I have, right? So if I insert a certain energy, you can see here that I'm just doing a small perturbation. As I make this perturbation smaller and smaller and smaller, what I have is that this log term here starts increasing, these parameters. And as you can see, the complexity really doesn't change at all until I reach times that are of order of the scrambling time. So these times here where this thing change is because of that. And again, from the gravity calculations, this really is how dominant certain terms are. So if I am in this regime, I have here that the dominant term is that the sort of the amplitude of how small this shock wave is the smallest number that I have. However, when I go to these other terms, because I have evolved TW a lot, that exponent becomes dominant. And that's why this changes and this starts growing again. Let's remember a little bit of what we thought about what the precursor should do, right? Because again, this really should be talking about how hard it is to construct these circuits. So what this is saying is that if I'm trying to construct this precursor operator at times smaller than the scrambling time, this is really cheap to make. So I don't really need to do anything extra to the thermal field double. But if I put this perturbation longer than the scrambling time associated with its energy, now I have to do extra work and I have to do this. So this is very nice because this really agrees with the expectation of the switchback effect. And also what's nice is that this also agrees even to the fine-tuning details, right? So this is something that Lenny also studied with Ying and Adden of how this Lyapunov exponent would increase here. And in this shockwave models, we can really see this explicitly, that I can literally just plot how even though you see from the past slide, this seems to be just constant, it actually is changing, but it's a very subtle change, so that's why you have to take the log of this plot, and we see that the log of the plot is just essentially, it's just a constant, and the proportionality constant is the Lyapunov exponent. Yes?
Yeah, so that's what I was going to ask. In what sense are you using the Lyapunov exponent?
Oh, no, here it's, again, there's this older story about, of course, Schenker, Stanford, where they calculate how the OTOC decays at late times, and they find a Lyapunov exponent that is given by that in holography. What I'm doing is a much simpler thing. I'm just comparing how this perturbation is growing with time. It's growing exponentially. This is the exponent. So that's the only way I'm using it. Yeah, so.
So on your previous slide,
Yes.
the thing that you declared feasible, is that in some sense assuming that some triangle inequality is accurate?
Yes, it is. Yes.
Why is that justified?
I think that's a good question, actually, that I think we should think more carefully. But a justification I can give you is that, well, this seems to be calculating the right complexity, right? Or at the very least, it's showing that this is capturing what the physics should be, and not only capturing the bulk of it, it's also capturing the details, right? So I think that's but in general, I agree that one should be more careful about.
Can you comment on how one might be more careful?
Yeah, I mean, I think one way to think about it is that at the very least, of course, this comes from holography, and then we are given this thing that's dual to complexity, and we're trying to explore its properties. So it's not very clear then exactly what are sort of like the norms that are associated with it. So there's some sort of additivity that one can talk about and things like that. In this subregion complexity, definitely there's a lot more that can be said about it. My perspective on it is that at the very least, this is giving me sort of like an interesting dynamics. And it seems to be giving me the right physics for it. So whatever holography is giving me, it seems to be telling a consistent story. So yeah. So I'll take more the opposite approach, that this seems to be the data that we have. So this might tell us something about how complexities are added in a sense in complexity causaction. Yeah, and let me just add that this plot that I showed, if I don't include these counter terms associated with the boundaries, I wouldn't find the switchback effect. So this is this type of plots that I would have. And as you can see, I would have that the complexity not only starts changing sort of right away, but nonetheless, it saturates and it becomes negative. And this really just be seen to tell me that this is not the right recipe, right? And so this is sort of like one very clear example that we had where this term not only seemed to be telling me about an ambiguity, but it's really giving me the right physics. So I don't have a lot of time, but I still want to talk a little bit about the QFT models. These in general are very technical and can get very technical, so that's not my idea here. My idea is just to show that we've been able to learn some interesting lessons from them. I'm happy to talk more about it during the breaks and during the discussion, so please ask me questions about it. But the idea is that, of course, in comparison to entanglement entropy, we don't really have something like the Carty formula had in the beginning, where I could show, at least for CFTs, that was giving exactly the same thing. So there's still a lot to be learned. What's the role of quantum complexity, both in quantum mechanics and in quantum field theory? So our idea is that we wanted to do a big step back and say, okay, of course, doing CFT and strongly coupled CFT is complicated, but let's study a simpler system. And one simpler system is just a free field theory. And let's try to see what notion of complexity exists in this context. Another thing that maybe from condensed matter point of view that should be thinking about this is these continuum meta constructions, so CMARA constructions, and that really was the starting point for a lot of this. That I can just construct these sort of like quantum circuits and tensor networks using the continuum. So the important thing here, we're going to use Gaussian states for these discussions, and I should really be thinking that I have a reference state that's just a simple state that has a large mass scale, so it doesn't have any interesting entanglement until a certain energy. And then the target states, they can be, for instance, the ground states of the Hamiltonian, or they can be some thermofield doubles. And the idea then is that if I think I'm doing sort of like a lattice system, I can think of the fundamental gates, just some sort of like entangling gates that I can construct with my X and P operators. So this is sort of like the ingredients that we have here. And then we're going to use sort of the algebraic structure that these gates they're going to have to be able to constrain the circuits. So being slightly more precise, the sort of things that we're thinking about is that I have this free Hamiltonian with field phi and pi. And again, mu appears as this reference state scale, and I should really be thinking this as a ultralocal thing. And then I want to calculate the ground state of this type of Hamiltonian here. Of course, there are separate ways of looking into this problem. One could start with simple harmonic oscillators and then take the continuum limit and get to theories like this. Or you could start already saying that, oh, I have these fields that are defined in this certain way, and I can just define. And so here's an example of the gates that we use, right? So it's these quadratic gates in momentum space that are local. And again, the nice thing about Gaussian states is that even though they have non-trivial correlations in position space, they factorize in momentum space. So then this is really good because we can solve the problem for one momenta and just integrate it over all momenta. So this is the sort of constructions that we have here. And then again, these gates that we construct here for each momenta, they're going to be an algebra. So we are actually able to construct geometries to it. So I'm going to give one of the examples here is if I just want to construct the ground state, it's enough to look at an SL2R algebra, or of course, it's also isomorphic to SU11. And then this is enough for me to construct the ground states of these Hamiltonians from these unentangled states. Here are two different procedures that one could consider in terms of minimizing the action. So this is in the Jefferson-Myers paper that really takes more the Nielsen approach, which is the one that I just showed, and minimizes for geodesics in that type of space. And again, this strategy here is just that I know sort of like what is a general element of this SL2R geometry, then I can construct a Riemannian manifold here, and I can look for geodesics, and I can actually calculate how this what is the length of these geodesics and find what is the minimum path. The nice thing about this problem is that it's really simple. You can prove that the geodesic is essentially just a straight line in this row coordinate here that I'm showing. So even though there are other directions that one could go and much more complicated circuits, the complexity is given by a simple path. The other thing is one thing that I've explored in this earlier paper as well, is that we try to study the similar problem, but with respect to a Fubini's 2D metric. So this takes sort of like the projective structure of the Hilbert space. And in general, these two can be very different. The global geometry can be very different. But it's interesting that, at least for this task at hand, they actually give the same integral. So we have the same result in the end. So the minimization sort of makes these two agree. And the thing that agree is this UV structure that I have here. Okay, I should wrap up soon, but I'm really finishing. So as you can see, when I calculate this in field theory, this kind of has a very suggestive, that's the word I use, similarity between the scales in my circuit model and what I had from holography. So as you can see, I always have here this reference state that is just this boring unentangled state, but I'm always free to make transformations to it. And therefore, the leading divergence of complexity in that case really also scales in the same way with that reference scale. And it's interesting that, again, it's suggestive that in holography, we also had this extra scale with the no boundaries that appear in the same way. Again, of course, this is not a derivation of the formula at all, right? We're just trying to learn lessons to see what type of properties the holographic complexity is really telling us. So the second thing that I told you is about the thermal field double state. And we can construct very similar circuits using these bosonic modes. Again, this is just for one mode, how one could use a squeezing operator to get the vacuum to the thermal field double. So again, it's really a very similar technology that comes into play. Actually, you can even show that if you go to a certain basis that this factorizes, and it's exactly the same geometry that one would consider. So you just change sort of like the end paths, but the minimization procedure really follows quite nicely. And then again, I can take what that is, and I can integrate it. And that would be, I can then calculate something like a complexity of formation. Because I have my vacuum complexity, I have the thermal field double complexity. And very interestingly, of course, there are many things that I can change in these complexity QFT models. But it's interesting that there is sort of like a natural choice that gives me an answer that sort of looks like what we get from holography, that it doesn't depend on the reference state that I had, this very massive, ultralocal massive scale, and it also scales like the entropy associated with the theory. And there's a coefficient here that depends on the dimension of space-time. We notice, however, that the dependence on dimension are very drastically different, that holography gives you essentially just a linear growth, while these models is giving me an exponential growth in the dimension. I'm not really sure how to interpret that. Maybe we're being too conservative here in our complexity construction, so that's why it's giving me a number that it's growing bigger than it should be. But again, we don't want to do a one-to-one comparison because that would be meaningless in this case. We just want to show that there seems to be some interesting story in these circuits that's telling me about these examples. And then this is my last slide, that unfortunately, when we were studying the thermal field double, of course, our goal was to try to see the late time growth of complexity. But I mean, in the end, when you're doing physics, it's not what you want to find, it's what physics tells you. And physics is telling us, I think it's something that we should be expecting, is that Gaussian states are simple. So there's not a lot of room for these two, other than, of course, the correlations that you have. But there's not a lot to be growing from that. So we do find in these Gaussian states, look that these plots are the complexity itself, not the derivatives. So we do find that they saturate sort of like of the inverse timescales. However, notice that, again, the way that it saturates is heavily dependent on what I choose to be my reference scale. Look again, mu which is that ultralocal mass. It appears here a parameter, and then the transient really depends on it. And again, and this is kind of similar how we had in holography, that even though the late time limit was fixed by the theory, and it was very general, it seemed that the transient really depended on sort of like the details. So again, not a one-to-one, exactly this shows that how our model is not capturing holography, but it's still interesting that the way that these ambiguities they play in a similar role. And I'm already over time, so maybe I'll just put here my outlook. And yeah, thank you very much for listening.